Hello, everyone. My name is Jialin. I'm from National Energy Research Scientific Computing Center, which is NERSC in the Lawrence Berkeley National Lab. Today, I'm going to talk about I/O topologies. I don't actually know what that means, but I try to share some interesting practices that I did over the years at NERSC in the Lawrence Berkeley National Lab. So the outline, I want to cover some common I/O issues in today's HPC I/O stack and the typical solution or some tricks we can learn to optimize the I/O. And with a little bit of focus and emphasize on the later two bullets, which is I/O performance versus I/O productivity, and also burst buffer. First, I want to make sure we are not here for talking about Indian Ocean or any really cool startup in Silicon Valley with the domain name .io. We are talking about keyboard, which is the input, and multiple keyboard, which parallel I/O, and multiple monitors. So that's important. I think that's related to our daily life, right? A lot of people care about I/O, especially in HPC, and the I/O will be more challenging in exascale. So I'm the guy who supports the I/O issue at NERSC. I often see these kind of questions. For example, your center claims that your peak bandwidth is 700 gigabytes. Why my application only gets 7 megabytes per second? Or very specifically, a simple question is, could you tell me how many OST should I use? How many storage nodes should I use to get better performance? And so secondly, some simple question like, why the ls in my directory never return? It's a simple question, but it's really complicated. And also, I also did some study to compare the Haswell and the KL, the new chip, Intel Xeon Phi, which is the multi-core, and also the previous 32-core Haswell nodes, and to see the I/O performance difference. And last but not least, I want to talk about the pain of productivity. So that means nowadays a lot of people try to use Spark, TensorFlow, or other big data analytics framework. But there's some pain of using that because the performance sometimes, especially running on HPC, is not ideal, it's not good. So we want to know how to load the data efficiently into the engine so we can perform the data analytics more efficiently. I should appreciate Philip Carnes and Rob Ross, all the experts, for sharing these slides. I think I learned a lot from that. So this diagram, this simple diagram really shows the complex I/O stack in our HPC architecture. That means from when you run your application, when you want your application to talk to the hardware, there are many layers you have to go through. And the number of layers is actually increasing. So for example, the productive interface, like a Python Spark. People just want to use really some easy and productive tool to do their work. They don't want to really use some, I shouldn't see it in that way, but most of the time, the C or Fortran is designed for high performance, but not really productive, right? But this complexity is one of the reasons that the I/O is hard to optimize and the tuning is challenging. And I/O challenges is more serious in next 5 years or 10 years. So we did a review on all the important scientific applications, like the basic energy science. We asked the PI of those projects, what do you see in the next 5 years or 10 years regarding the data volume and the storage requirement your group is going to need? So a lot of PI responded with some estimation, and this study was done 3 years ago, and I think I don't really feel surprising about the number because the data increasing is much larger than those PR expected. So for example, in 3 years ago, if you have 100 terabytes on your Scratch, 100 terabytes data on your Scratch, in 5 years, they expected to have 350 terabytes. And then in 2025, it will be 2.2 petabytes. So the data volume is just huge, and it keeps increasing, keeps stressing our storage file system. A third point a third maybe background point I want to bring to you is overall storage architecture, typical storage architecture we have. So the fact is that the resources, our storage resources, are shared by all the users. So on NERSC, we are supporting 7,000 users. So all those users from all over the world, they are trying to use the same storage server. Basically, no matter how large it is, it's shared. And over the time, the storage gets full. You have less and less space left on the storage side. And the performance is decreasing. Some of the reasons like fragmentation or contention on the server. So the I/O is challenging, and given those background or context, I will jump into the common issue that we saw and some tricks we can do. So how many OST should I use? I saw these questions every day, and I don't really know how to answer because it's really complicated. And given a specific question, I usually take 2 steps. First, I try to identify the user's, the application's I/O pattern. Try to figure out if it's a really bad I/O pattern, sometimes random, small, non-contiguous. In that case, I wouldn't expect really good bandwidth number. I would just be honest to tell the user, maybe you should redesign your I/O, redesign your code. And the second step, it is really simple to check the stripe count. That's a really simple trick that we can potentially easily optimize, increase the I/O bandwidth. So
what does that mean? Check your stripe count. Stripe, I don't understand.
Okay, here's the answer. So here's the basics about the striping. Striping is about to store your data on multiple storage servers. By default, your data will just go into one storage server. So striping is to using more resources to serve your application, to serve your I/O requests. But it doesn't really help all the time, because imagine that your file is very small, like 1 megabytes, and you store that on 100 storage server. What could that be, right? Every of your requests, if you are reading all the file, will go to 100 servers. And if one storage node is very slow, then that slow node will dominate your overall runtime. So that's the extreme case. On the other hand, you don't want to store 1 terabyte of data on just one OST. So we do have some recommendations, but mostly are empirical recommendations. For example, if your file is less than 1 gigabyte, you do nothing, because we consider that as a small file, and you just use one OST. If your file maybe very large, larger than 100 gigabytes, you try this command, stripe large. Behind, we changed the number. Now I think it's 72 OST. But like I said, these are empirical recommendations. Most of the time, I will recommend the user to do some small-scale tests. So try 2 storage server, and then compare with the default striping. Or maybe then try 4 OST and 16 OST. So based on your application, based on your exact I/O pattern. Try to tune by yourself. It's very simple. Just use the command lfs set stripe to configure the number OST.
What do you mean by OST?
Oh, that's a good question. I think here it is. This is the OST, object storage target, and this is object storage server. So basic one OST consists of a lot of disks. That's the concept, a term used frequently in the raster file system.
So if you're only using one OST, you basically don't have any parallelization across the I/O interface, or do you still have some parallelism there?
There is some internal parallelism on one OST. Yeah, there is some, but not ideal, not good as good as we expect. There could be also some parallelism from clients. Mm-hmm. Yes.
So if you use multiple OSTs, would the memory consumption increase?
I mean, the number of OST doesn't matter. So your memory consumption really relates to your application, right?
Okay, so it has nothing to do with, so if I increase the number of OSTs, there will be no extra memory overhead.
Right. Mm-hmm.
So would I, even though my files might be small, shouldn't I try to use as many OSTs as possible?
If your file, depends how small. So if your file, like we showed here, less than 1 gigabyte, just use default striping, just one OST. But sometimes you can see better performance with 2 OST. The reason we recommend just one because we consider that this is the center for 7,000 users, right? So,
That makes sense.
yeah. And second issue is the metadata. So LS is too slow. And this is tickets I received every day. So Harry is some of my previous colleague. So note the LS fund still hasn't returned as a very specific time. So, and some other ticket, similar issue. So then I did some study. We did some study to really figure out why the LS can be an issue. So it turns out on HPC software stack is a little bit complex. So the LS goes through multiple paths. The path includes multiple hubs, from raster client to the LNet router, and then to the metadata server. And sometimes it will also go to the hundreds of object storage servers. So one query, if it goes to all the paths to the object server, you can imagine the overhead, the communication is larger than simply querying the metadata server. And we should keep in mind that there is some difference between those commands. And also the stripe count also matters. If you have 48 as a stripe count, and you do ls -l, and you query 60,000 files, so all the query will go through LNet router to the major single metadata server, and then go through hundreds of storage server, 100 object storage server. So that's for single query, and you have 60,000 query. But for one, if you set the stripe count as 1, it will just go through LNet router, metadata server, and 1 storage server. So the query can be returned relatively faster. So that's the details about the LS on Cori, and it turns out to be really CPU intensive and random small I/O if we care about the I/O pattern in this kind of query. And typically, we recommend the user to check the weather. The weather, I like the term, but I think I steal that from Philip Carr's project. So I think maybe they have nice work coming out. Basically, we have a lot of monitoring information available on our system. So you can check the MOTD, the center's general status and file system monitor and some benchmark. Basically, some application, we run that every day, and we report the number through this web browser. And the data dashboard to check how many users are in the same group, how much data you have, how many nodes that you have consumed, and also the weekly email that we send out. So here's the example of the file system monitor. So you can see this is basically we run the LS every day. We report the cost. You can see some day it's really bad, like July 23rd. There can be many issues. Some storage server may die, or the number of users just on that day, they are so happy to use the system, they cause a lot of traffic. So check those weather before you do some heavy I/O operation. That will be helpful. And the third issue is about the difference between the two CPU chips, KL and Haswell. So, typically, the I/O bottleneck has nothing to do with the CPU speed, right? The CPU is so fast, so your I/O subsystem is the major bottleneck. The CPU shouldn't be the factor that impact your I/O speed. But everything is changing. I think due to the complex I/O subsystem, we observed as much as 4x performance gap between KL and Haswell. Even when we change the CPU frequencies, like on the right figure, you can see that we slow down the Haswell CPU from 2.3 gigahertz to maybe 1.2 gigahertz. We purposely slow down the faster CPU and to match the slower KL CPU, but we still observe the performance gap. That is a mysterious issue. And then we continued the study. Basically, we did a lot of tests on a single core. And we observed actually the difference is much larger in the default buffered I/O. In default buffered I/O, you have a lot of memory management and the buffer and page cache management involved. So from your CPU, from your cache down to the storage server, there are multiple layers. And if you just use direct I/O, the I/O goes from your user space to the disk level. So in that case, the difference between the two chips is much less than the default case. So we concluded that the memory management and buffer management on the KL chip is just slow. But for more details, I encourage you, if you are interested, you can do some interesting research along this direction. So after this study, we did find some optimization techniques like a core specialization and process affinity. Try to leverage the multi-core on KL. For example, use one core on KL to do the kernel stuff, not bother with the application. Or if your node is not fully packed, you try to balance your load across all the cores. So that takes sometimes help. And the fourth issue is about the pain of productivity. So personally, I really like Python and TensorFlow. I did some work on Spark, but there's a lot of work to be done to really run Spark efficiently on HPC. So the issues that I care about is how we can load the HDF5 data into those big data framework. Why HDF5 or PNetCDF? because a lot of our science data are stored in that format. We don't want to reformat 100 terabytes of HDF file into some text file and create a copy on the storage, and then just to use Spark or TensorFlow to load that data, right? So we want to figure out how we can load HDF5 or PNSDF or audios, those scientific formats data efficiently. In most cases, we found that H5 is very useful. For example, even though we designed H5 Spark, but that's based on H5 And we also explored a little bit on the TensorFlow I/O, and now all those codes are open source. You can try that and play those software on HPC now. And we observed the increasing number of users of those productive software. So we monitor the number of software usage every day. For example, this is a daily H5 unique user from 2017 to just a few days before I came here. So you can see that actually it's increasing, but this is the number of unique users every day. So if we count the total H5 users, we saw that the users are increasing from just 10 to 80, and nowadays is 360. So a lot of users like to use those productive interface. And similarly for NetCDF Python, there are hundreds of users nowadays. Why people want to use that? I think it's just because it's very simple. So for parallel H5 3 lines of code can save you a lot of time if you want to use and leverage parallel I/O. For example, independent I/O, nothing. You don't see where we can specify the independent I/O, like the MPI I/O, right? And then for collective I/O, just with this with dset.collective, then collective I/O is turned on. So it's very simple to use, very productive. So in terms of productivity, this is the code comparison. If we implement the same algorithm, same I/O stuff, using the two software, one is H5, one is HDF5. The left is H5, right is a C language. So the first block matches to the whole page on the right. And second block matched to another page on the right. And then the last few lines, you will need multiple lines on the right. So this definitely shows that using those software can increase our productivity. And similarly for Spark and TensorFlow, if you try this H5 Spark that I designed 2 years ago, it just took 3 lines instead of this page of MPI I/O. But for performance, that's a different story. So there is some trade-off. We compared the H5 and the HDF5. So in most cases, it seems that H5 is close to HDF5. In some cases, like metadata heavy, you create a lot of files, you query a lot of objects inside the file, or in some cases, like there's a lot of communication across multiple nodes, the overhead is much larger. That's mainly because there's some overhead in the Python layer. There are also some optimization work on those layers, so we could expect much better performance in the future. Yes?
In which case do you want to use independent or collective I/O?
Can you say that again?
In which case do you prefer to use independent or collective?
I think collective I/O is designed to optimizing non-contiguous I/O. So in case of large contiguous, like streaming I/O, most of the cases you found the independent I/O is much faster, right? It's simple, much faster than the collective I/O, less overhead. Okay.
So you can use this. Let's say if I was writing my program in Python Fortran, I can still use Pi.
Fortran? No.
I mean, so let's say you have an application code in C++, and you want to handle I/O. You use Pi to handle I/O. I'm sorry.
Okay. That will be a little bit complex because you are using a lower level language to call a high level language, right? You are using you will need to use C++ to call the Python package. That's typically the opposite way of people doing nowadays. People try to use high level language like Python to call C++ or C, right?
Okay.
But you still can do that, yeah.
So essentially, I have to write something in Python to call C++.
To be called by C++.
Just go ahead and use HDF5 directly. Like
Yeah. So
H5 is just Python handlers, or it's just
Like a wrapper.
Yes, but on top of everything you developed, you can try to use Python to call this C or C++. That's relatively easier. Fortran, I haven't done a lot of work, but I can ask one of the Fortran experts. Yeah. Yes.
So this actually goes back to striping. So I want to clarify, I've got like 100 gigabyte data set and I want 10 OSTs. How is it going to distribute that? Is it like serial, first 10 chunks on the first OST, like the next 10 gigabytes on the second OST? Does that make sense?
You're almost right. So with apart from stripe count, you also have another parameter, which is the stripe size. Stripe size is, in most cases, you can set as 1 megabyte. In your case, you just set 10 gigabytes, right? So in most cases, you set it as 1 megabyte or 4 megabytes. That's the unit, striping unit. So you can, your data, your 100 gigabyte data will be written as 1 megabytes across all OST and round robinly.
Okay.
Mm-hmm.
Thank you.
Good question. Yes.
So we all know that Python is slow, which is probably why the metadata processing takes longer. But my question is, so perhaps I'm using the Python with HDF5 and most likely I'm using HDF5 because the data is too big and I want to process it in C++. So I can create C++ script code that will run in Python. Like Python wrappers around the C++ code. Is there a way to send this data to that function from Python? Or is the way we load that data exclusively with your library exclusively limited to Python?
That's a good question. If you use H5Py, those details you don't want to won't bother you because the data from on disk will be loaded into a NumPy array.
Yes, but basically, so I could, because, yes, but then processing will, like if it's large chunk of data which is easy, the processing in Python will take forever. So I need to process it with like low level C++. But then I can send, I think I can probably, you can create a wrapper around the C++ function and NumPy array. Okay, that's my question.
Yes, actually I'm doing some similar work nowadays. I try to, but you really want to avoid the memory copy. In most cases, you just can't. You just can't avoid the memory copy because in Python there's no pointer, so you can not directly pass along the pointer. But Python nowadays does support, not nowadays, I think it has been supporting the pointer object. So basically, if you have a C pointer or C++, there is no pointer in C++. If you have a C pointer, you can pass that pointer as a Python object. So Python will interpret those objects. Those objects, clearly it will be larger than your original buffer, right? Because it contains some metadata information. Yeah, sure. So the last section is about burst buffer. It will be very interesting because in the next 1 hour, you will gain some hands-on experience on those burst buffer. So this is the basic architecture. On the right is the typical, our traditional raster file system, but nowadays we added these burst buffer nodes, and it's connected with HSN, with Cori's computer nodes. And we have 288 nodes, 46.4 terabytes each. So there's some details about how burst buffer works. So basically, when you launch your application, the Slurm scheduler does the secret job. It will create, based on your request, capacity request, it will create a DataWarp space on top of the burst buffer nodes. So, and mounted that space to your computer node. So your computer nodes can see that as a POSIX file system. And you can create 2 different DataWarp instances. So one is a per job instance, the other is persistent. Persistent instances means you can use in multiple jobs. And you do have 2 different access modes. One is striped, which is recommended. And in this access mode, your file will be striped across DataWarp nodes. And the second is the private. It's a little bit hard. It's a little bit hard to explain, but in most cases, striped access mode is recommended. I should say I just don't understand the private access mode. It's not hard to explain. So from my understanding is that when you create data space, each computer node will own its own DataWarp space. So the DataWarp space is not striped across all the nodes. In theory, the performance is better than the striped shared mode. In case our modes use the striped pattern. And there is striping similarly to raster file system, but a little bit different. So the striping on burst buffer allows you to specify the capacity of the burst buffer resources. And given that capacity number, the DataWarp will return will retain the burst buffer nodes to satisfy this capacity request. For example, if you request 1,000 gigabytes and the granularity of the allocation is 20 gigabytes, then you will get 50 burst buffer nodes. So this diagram shows how burst buffer works. So when you launch your application, you request the capacity. You basically ask for some burst buffer nodes to be used. And you can also specify whether you want to stage in your inputs onto burst buffer. If you specify the staging path, the data, before your job running, the data will be first loaded from the raster file system to the burst buffer nodes. And then your job starts to run on the computer nodes. At that time, your job can access the data on the burst buffer nodes. This is how it works. And you can the stage in and stage out has advantages over the simple CP command, copy command, because if you run the CP command on computer nodes and copy some data from the raster file system onto burst buffer, the data will go through the memory on the computer nodes, which is costly and not necessary. But if you use stage in, the data will just go from storage server directly to burst buffer nodes. So you want to avoid this double copy data path. And how to use DataWarp, we will cover more details in the next hour. And they also offer some C API that you can use in your code. So, but typically, people just use this environment variable in their batch script to specify the stage in and the stage out. So, yes, any questions?
Yeah, I was just wondering how much faster is this over the regular?
HDD raster. Here's the number. So you always ask the correct question. Burst buffer is really fast. Probably the fastest I/O system in the world. So we did some tests with the simple IOR benchmark. And if you remember, the peak bandwidth on our raster file system is 700 gigabytes. And on burst buffer, we can achieve 1.7 terabytes per second. So there is a burst buffer early user program 2 years ago. Basically, in that program, a lot of application team come to the center to use the burst buffer. And here are some successful stories. So in this Chumbo Crunch and Visit IT story, they compared the raster performance and the burst buffer performance. So burst buffer outperforms the raster clearly in all the different file size tests. And second story, Atlas. And the third story is from Astronomy field. So I'm familiar with this one because this is my first year project at the Lawrence Berkeley National Lab. So in this case, the I/O pattern is very random, and the number of files is millions. There are millions of small files. And we found that on raster, we tried a lot of optimization techniques, even some not in a stable version library, but we're still not satisfying with performance. And then we tried on burst buffer with just a few simple commands, and we got 33 speed up. So if you have some codes on hand, in the next hour, you can really play with the burst buffer using your own code. Otherwise, I can provide you some simple IOR code or H5 code. You can try that on burst buffer.
Sorry. Is this speed up only taking into account the I/O
Yes.
time, or have these algorithms like run for hours or something like that?
So we extract the I/O kernel. Especially in the last case, the analytics is relatively fast. So the I/O is a major bottleneck. Yes, question?
So just very basically, can I think of burst buffer as just another higher level of shared memory for the users, just treat it like that?
There isn't any additional level. So it's just like a traditional POSIX file system. So burst buffer is just separate hardware nodes. And when you create the DataWarp space, instead of going to raster file system, you go directly to the burst buffer nodes.
So they're ordinary compute nodes?
Computer nodes is the same.
Same kinds of nodes, just designated nodes for I/O.
Right, exactly.
For same capacity, what is the cost ratio between burst buffer versus raster file system for the same capacity?
That's a good question, but I don't have the number for you.
Well, is it a lot more expensive, like 10x more expensive, or 100x more expensive? Do you have a rough number?
The price for for SSD is keeps decreasing over the years. Yet, I think maybe in the next few years, the cost ratio they will cross. Yes.
Do you have any reliability concern over SSD? Because HPC application is different, right? So
Right.
all real writes, will that cause any pressure to SSD? And do you observe any significant failures or often failures on SSD?
That's a really good question. So we are doing some research and study on the lifetime of SSD. So like you said, HPC workload is very complex. In most cases, we are worried about the bursty I/O pattern, right? And if it is not well balanced, it will just go to a few number of SSD. And the garbage collection, the overhead, and all the stuff will reduce the lifetime of SSD. We don't have exact number, so we are trying to monitor the usage of burst buffer. Yeah, but that's a really good direction to consider in the future.
This burst buffer, like the idea is like it's always a temporary file system, right? So like, if one stops working, you just put in a new one. And, like obviously, like if you're running something that it'll fail, but like the idea is like it's almost like a cache, right? Kind of thing.
That's an interesting question. You can create a persistent instance, and it will stay there until you delete that. Yeah, with that persistent instance, you can use that as a scratch file system. What's the second question?
No, I was just like wondering, like, yeah.
Oh, but you mentioned the cache, so that's an interesting point. So I think in the fall of this year, there's some change on the burst buffer architecture. In that case, the burst buffer will be used as a transparent cache. So in that case, you will not need to do anything to use that. You can just run your application, and your data will be first written on burst buffer before flashed to raster file system. That would be awesome, right? In that case, the burst buffer is the cache.
Yeah.
Yes. Yeah.
On the last slide you showed, why do you have so much loss in performance when using the burst buffer when switching from the HDF5 to individualized time? Like 30 times when the other cases or
because HDF5 is this version of HDF5 format is the optimized version over the FITS file format. So in case of reading FITS, the I/O pattern is really bad. So it's not, the I/O is the same, but the file format determines how much data you can load each time. And it turns out when we read the FITS file, the I/O transaction size is much smaller than the HDF5 file. So along that direction, I would really recommend you to come to the Darshan session. I think Phil will talk about how to really profile I/O, profile those transaction size to understand the performance difference.